Okay, hello again. This is the first video in a new section, section 10.3. This is a new material after the break. Complex numbers in polar form. And we're going to lead into De Moivre's theorem, and we're going to probably have several videos, shorter ones, on this topic. Okay, so let's go through some of the basics, and we'll see how this works out. Okay. We have the real axis. We have the imaginary axis. And what this is going to deal with, or the y-axis, what this is going to deal with is plotting and working with complex numbers in polar form. So let's pretend we have a point here. This would be the point 3, 2. But since this is the complex plane, here's how we're going to write this instead. Back. Let's just think about this. You got I, 2I, 3I, negative 1I, negative 2I, negative 3I, and so forth. And this would be 1, 2, 3, negative 1, negative 2, negative 3. So a point here would be 3 is the real part, and 2 is the complex part. So this would be 3 plus 2i, all right? And what we're going to typically do here is we're going to typically learn to plot some points. So a point down here would be, let's see if we can figure this out. The real part is 1, complex part is negative 2i. So this would be 1 plus negative 2i or 1 minus 2i. And that's how this is going to work. Now what we want to try to do is we want to try to expand this and write these in polar form, because there's an interesting set of operations that we can do. So let me start again. And this time, we're going to see the type of familiar diagram we've seen many times in the past. Okay, so this is going to be our complex A plus BI. Okay, and typically the complex variable is represented by the letter Z. So if we bring this down, and again, this is our real axis, this is our imaginary or our y-axis, and instead of using x's and y's, what we typically do is we use a's and b's. This is symbolized by R, which is called the modulus. Okay, so here we go. Let's write down, and we've got theta, of course. So what we're going to do is express this in complex form. And some of the relationships that you need to know, we've seen this in the past, is absolute square root of a squared plus b squared. And in complex, what we do is we simply put absolute value there, and this is called the modulus. Okay, and theta, well, just like before, see arctan, instead of y over x, it's b over a. And kind of amusing, but the theta is called the argument. So if I use those words, then obviously I'm not trying to be funny, but this is called the argument. This is called the modulus. Okay, and just like before, we've had certain relationships. So let me show you what they are. X, we used to write x. Now we're going to write a. It's r cosine theta. And we used to write y. Now we're going to write b. Is r sine theta. So all of these relationships that we've had in the past are going to hold true. Okay, so typically, if I go z equals a plus bi, I can replace the a by r cosine theta, and I can replace the b by r sine theta. And of course, I've got the I there. And by the way, you should know this, but I square root of negative 1. So this is our complex. Z is going to be our complex variable. So if you see a Z, typically means in most mathematics that that's complex. So what we typically do is we typically factor out the R, which is in both. So we have cosine theta plus I sine theta. And this is called the polar form of complex numbers. Now, it seems like a lot to write out, so there's an abbreviation. The abbreviation is we take the C from here, the I from here, the S from here, and we write cis theta. And of course, we bring down the R. So this is something called cis notation. And if I get tired of writing something the long way, I will write it in cis notation. And that's pretty much about all I need for the introduction. So give me a few moments, and what I'm going to do is I'm going to erase this, and then we're going to do some numerical examples. Okay, so let me erase this, see how that goes. All right. This is working great. All right, so here we go. All we're going to be doing is expressing complex numbers in polar form. So the instructions will be convert into polar form. So example number 1 is 1 plus I. And I think you know me by now. My process is I make a diagram. So 1 plus I would be right here. Okay. And we're going to complete that. That's our R. So in this case, you can see A is a 1 because don't forget, Z equals A plus BI is a standard form for complex numbers. So in this case, we can see A is a 1, right? And B is the coefficient of the I term is also a 1. So that's why I drew it the way I did. Okay, so what we got to get is our common theta, and clearly then R, well, you can do this pretty easily here. R is 1 squared plus 1 squared, so R is a radical 2, okay? And in realizing that the A and the B are 1s, you realize this is 45 degrees. So this worked out kind of nicely. Okay, so we get that Z equals 1 plus I is, we're going to put this in that special form. The special form is R cosine theta plus I sine theta, right? So it's going to be R is radical 2 cosine of 45 plus I sine of 45. Okay, so that's how we would write 1 plus I in polar form. Okay, and just as a reminder, it's R cosine theta plus I sine theta, and that would be our polar form. So that's pretty easy, okay? All right, so let's just keep on doing. Oh, and by the way, if it turns out that you want this in radians, and of course, pi over 4 is the same as 45. And don't forget, you need the parentheses, because the radical 2 is the R of the modulus multiplying the entire expression. So either this expression or this expression would be perfectly acceptable. Okay, let's try another one. Okay, so example number 2. Let's try radical 3 minus I. Okay, so I'll give you a few moments. And typically, what we would do, I would call this Z. Okay, and let's not forget the basic form is we want R cosine theta plus I sine theta. So we want to get our result in this form. Okay, so again, I'm going to basically make a diagram. Okay, and I'm going to realize, let me put this over here. Z equals radical 3 minus I. Okay. And let's see if we can figure out where this is. Okay, the A is radical 3, and B is negative 1, so this is the real axis, the imaginary axis, so we're going radical 3 minus 1, so this would be your radical 3, this would be your minus 1, so this would be the point 3 minus 1I. And, you know, we've done this many, many times. So we're using Pythagorean theorem, radical 3 squared plus negative 1 quantity squared, radical 4. So this will be a 2. So you can clearly see that R is a 2. Okay, so what we're doing again, R is square root of 3 squared plus negative 1 squared, all under radical. So this is a 3 and this is a 1, so R is the square root of 4. So we get that R equals a 2. So our modulus is 2, and you should recognize what's going on here. This is a 1, well, a 30, 60, 90. Your reference angle is 30, but let's not forget it's in quadrant 4, so it's actually 330. All right, so we write this down. R is a 2, and the angle will be 330. So it's cosine 330, whoops, plus I sine of 330. And this would be how we would write radical 3 minus 1 in complex form, in polar form. Okay, so you could also write this as 2 cis 330, which will be fine. I think this would be 11 pi over 6. Is that right? Yeah, that would be right. So you can also write it as 2 cis 11 pi over 6. There are multiple forms. This is what we're going to deal with most of the time. Okay, so let's just continue and do a couple more examples. And don't forget, you can pause the video, you can go back. So my erasing it here, it still is actually viewable. You can go back and look at this if you want. These are pretty easy examples that I'm doing, basic stuff. And we'll learn how to manipulate these when we get to Dumoir's theorem. Okay, so let's try negative 2 plus 3i. Okay, and hopefully you're going to be looking at that, and you're going to be realizing that's in quadrant, I hope you can see it, quadrant 2. So let me make a quick sketch. So this is the y-axis, the imaginary. This is the real axis, so negative 2 up 3. So 2, 1, 2, 3, right? This would be 1i, 2i, 3i. So you'd be about right here. Okay, so this would be negative 2 plus 3i. And we go through our typical routine. Okay, this is a negative 2. This is a 3, and you can easily compute r. Okay, so r would be negative 2 squared plus 3 squared. So r would be radical 13, right? This is 4, this is 9, so r is pretty easy to get. Now the problem is, this is not a special right triangle. So what we're going to have to do is we're going to have to do an arctan. Okay? So what you're going to do then is, this is a calculator type. Okay? So you're going to do theta is arctan of negative 3 over, negative 3 over 2, right? Boom, boom. And you're going to put that in your calculator. And what you're going to do is you're going to get, hopefully in degree mode, I think that's the best way for us to work. And you're going to get approximately, let's say we do this to the nearest degree, negative 56 degrees. Now, this is going to be a little bit of a problem for us, because clearly looking here, that's not negative 56. And you have to be a little careful when you're using arctan, because don't forget, we get this idea of principal value. So where is tangent negative? Tangent is negative in quadrants 2 and 4. So what this is giving you is the principal value. So if it's negative 56, right, what you have to try and imagine is the principal value. Here's your negative 56. And you sort of have to realize, well, gee, I'm in quadrant number 2 here. So this is not going to be a negative 56 for us. It's going to really be, well, here, let's actually do it. If this is negative 56, these angles are congruent because they're angles formed by intersecting lines. They're called vertical angles. So that means that this is 56 degrees, and the angle that we're really looking for is this angle here. So if this is 56, you got your 180 less 56. So rounded, that would be 124. So theta would be 124 degrees in quadrant 2. And we would then write radical 13 cosine 124 plus I sine 124. Okay, so it is going to happen occasionally that this would be our result, our complex number, negative 2 plus 3i in polar form. So we have to understand that sometimes we are going to run into these issues, and don't forget, we have to think about principal value. Okay, let's just keep on going, and we'll do another one, and hopefully we can see some insights from there as well. So let me erase this, and we'll do example number, I guess this is example number 4. So I have to change that. Okay, this is working out well. Okay, so example number 4 is negative 2 minus, oops, not negative, it's 2 minus 2i radical 3. Okay, so in this case, hopefully we can see that A is positive 2, right? If you forget the I part, then B is negative 2 radical 3. Okay, so this is going to turn out to be not so bad for us actually, okay? Okay, so again, let's make a sketch. You got the real axis, you got the imaginary or the I-axis, and looks like A is 2, B is negative, so we're quadrant 4. Okay, so This is not going to be to scale very well. Sorry about that. Okay, so this is 2, negative 2 radical 3. And here's our theta, and theta is in quadrant 4. So what we're going to do is let's get R first. Okay, so let's get R. Okay, and that's going to help us a lot. So you get R is 2 squared plus negative 2 radical 3, the quantity squared. Okay, so this is 4. This squared, well, let's just do it quick. We don't need to worry about the sign. If you square this, you get 4 times radical 3 squared, you get a 12. So that works out nicely. So square root of 16 is 4. So this length is a 4. This length is a 2. And this is negative 2 radical 3. Okay. Now actually this is a special right triangle. Don't forget it's relationships. It's not memorizing numbers. Normally we would see the 1 and 2, the radical 3, but let's not forget the basic idea is in a 30, 60, 90, the side opposite the 30 is half the hypotenuse. So we got that ratio going on here, that this length is half of that length. Therefore, this would be 30. Therefore, this would be 60. And since we're in quadrant 4, that would be 300 degrees. So you get z equals 4, which is the modulus. Okay. And cosine 300 plus I sine of 300. Oops. Parentheses go here. Okay. So that would be how you would express that in polar form. Okay, number 5 is kind of easy to do, so we don't even really need a lot of space. Let's suppose we want to express negative 3i in polar form. Well, that's not so bad. That's pretty easy, in fact. You just make a sketch. Negative 3i is right here. Okay, so it's down 3 units on the imaginary axis, and that's why it's negative 3i. And it's clear, I mean, this length r, because it's on one of the axes, is just a 3. And the angle, well, it's 270. So this would be 3 cosine of 270 plus I sine of 270. And that would how we would write negative 3i in polar form. All right, so let's see if we have time for one more. Okay, let's do, all right, let's do a couple where we go the other way. All right, so let's start with something in polar form and see if we can write it in a plus bi form. It's always good to go back and forth. I mean, just in cars, we have forward gears, we have a reverse gear, so you could get out of trouble as fast as you get into it, right? So this is example 5 for cis 150. So now we're taking that shortcut. You could also write it as 4 cosine 150 plus I sine of 150. That's the same thing. And the idea is now we want to express in a plus bi form. So we're going from polar form of complex numbers into a plus bi form. So again, I'm just going to make a diagram. And, we've done this type of thing many, many times before. So this is your real axis. This is your imaginary axis. 150 is something like this. So this is your 150. degrees. Okay, so you got a reference angle of 30. It's always nice when you get that. Drop a perpendicular. And two ways that you can approach this. You can simply put a 4 here. Okay. Yeah, let's actually do that. So let's put a 4 here. And the idea is in a 30, 60, 90 to slide opposite the 30's half the hypotenuse. So this would have to be a 2, right? And then this would be 2 radical 3. And of course its orientation is to the left. It would make it negative. Okay, so moving along, and that's pretty easy to do. I mean, the answer is right there. The x value, or the a value, is negative 2 radical 3, and the I value is positive, and it's a 2, and the thing you can't forget to do is to put in the I. Okay, so 4 cis 150 would be equivalent to negative 2 radical 3 plus 2I. Okay, one last one, and then we're going to hang it up for this topic, and then we'll move on to de Moivre's theorem. So, example number 6, and this is the last one, will be 4 cis of 240. So let's just change the angle. In fact, let's write it a different way. Okay, so let's pretend we wrote this in this form instead. Well, most students prefer working with degrees. Pi is 180, pi over 3 is 60, so this is 240. So cosine of 240 plus I sine of 240, and you got the 4. So clearly we're talking about right here. This is 60. The R is a 4. The R is a 4. So let's see what happens. Psi opposite the 30's half the hypotenuse, 2, got to be a negative. This would be 2 radical 3, got to be a negative. So this would be negative 2 minus 2 radical 3i. And that's how we would write that in A plus BI form. Okay, thank you.